Okay, so up to this point, we've assumed that the population standard deviation that we call sigma, has been known. So even if we go back to this prior example, let's go up here, we're just told that the standard deviation is 0.02 inches. It's just known. But in reality, that's generally not the case. So we will likely not know what sigma actually is. And we'll need to estimate that with our sample standard deviation, which we call S. So because of this, we're actually going to need a new statistic. By that, I mean we're going to start using something we call the t-statistic rather than what we've been using, the z-statistic. So let's go ahead and examine our new formula for the confidence interval. So this is for when sigma is unknown. So previously sigma was known, now it's unknown. So it's still just a point estimate plus or minus margin of error. But now our formula is x bar, our point estimate, plus or minus. So t, n minus 1 degrees of freedom, alpha over 2, and then s over root n. So let's take this piece by piece. There are two differences here. One is that we are using s instead of sigma. And the second difference is that we are using t instead of z. Okay, so we now need to talk about the t-distribution. So my drawings are never very pretty, as you are well aware of at this point. But essentially the t-distribution is that it's the normal distribution. It's the normal distribution, but for smaller sample sizes. And in fact, we're going to have a unique distribution for each n. So what we're going to do is we're going to take our sample size and we're going to subtract 1. So we're going to say n minus 1 degrees of freedom, and we're going to look at the corresponding t value. And we'll note that as n increases to infinity, t actually starts to approximate the z distribution, or the standard normal distribution. So what I mean by that is here we've got the z distribution. This is what we've been working with up like through this class. But these other curves, for example, the blue curve represents 10 degrees, the t distribution with 10 degrees of freedom. And notice how it's quite flat, and there's less area centered around or 0, and there's more area in the tails because it's more dispersed. But when we increase degrees of freedom to 20, we start to see it gets closer to that z curve. It's a little bit more, or a little taller, not quite as wide, but it's still wider than the z distribution. So you can almost think like some hand is like coming down and just like pushing downward on this curve until we get these other distributions. So we can note that the t distribution is flatter than the z distribution. But t starts to resemble z the more closely as our sample size n and degrees of freedom increases. And so we actually have a separate table for the t distribution, and it looks like this, and this is posted on Schoology. So it looks very similar. Notice that we now have a critical value of t here instead of z, and we're looking for area under the curve, so this area right here. But this table is actually easier to work with because it's providing us areas for this whole big area, this green area over here. And it's also giving us the area, this blue area over here, which is calling alpha. And that's what these represent. So this is going to be really useful for creating confidence intervals when we need to look up t-values. And then we can see we've got degrees of freedom over here. So for example, 5 degrees of freedom would be this row. So we would look at that row. Or if we had 10 degrees of freedom, we would use this row. So let's just do a couple quick examples with this. So let's say I want t 5 degrees of freedom, 0.025 in the right tail. So what does that look like? Okay, T5, 0.025. So I'm going to go down. I'm saying I want 5 degrees of freedom, so I'm going to use this row. So 5 degrees of freedom, and I wanted 0.025. So 0.025. So I'm going to go down to here, and I'm going to use this value, 2.5706. So 2.5706. Okay, now let's do T20.025. Okay, well now I'm going to use 20 degrees of freedom, so I'm going to use this row, 20 degrees of freedom. But I still want 0.025, so I'm still going to be using this column, and so I'll take this down. And I see I get the value 2.086. Okay. Let's do a couple more. So let's do T6.01. So 6 degrees of freedom, 0.01 in the right tail. Okay, so T6.01. So I'm going to go down to 6 degrees of freedom, and then I want 0.01 area in the right tail. So I'm going to go to 6 and then 0.01. So I see that's going to be 3.1427. So 3.1427. Okay, last one. Now let's do T21.01. So now I'm going to use this row, 21, go over, and I'm still using 0.01 for my tail probability. And I get 2.5177. So 2.5177. And that's how we use the t-table. And other than that, I mean, this is all pretty much the same in terms of how we're going to calculate our confidence intervals. Right? This formula is very similar. We're just now using this new t statistic and t-table instead of z. And then we're just going to use s instead of sigma, which is just the standard deviation from our sample. So anyway, next video, we're going to actually do a couple confidence intervals when sigma is unknown.